Hi everyone, welcome to our video lecture on section 8.4 dealing with trigonometric substitution. This one will be the third integration techniques that we have been learning so far, and in this video lecture we're going to be evaluating integrals using the method of trigonometric substitution. To motivate this topic, I want you to consider the integral from -1 to 1 of the square root of 1 minus x squared dx. Can we integrate this one here with the techniques that we've seen so far? Well, this one here doesn't quite look like an integration by parts problem, so maybe a u substitution could work. If we'd go ahead and define the u to be the radicand, well then you would see here that our du is going to have a negative 2x, but that's a problem because, well, what can we do here with this x? Alright, so a u to substitution doesn't quite work. Nonetheless, I would argue that you guys would be able to figure out this integral without using any of our integration techniques. We can actually take an easier approach and think about this problem geometrically. Now, what do I mean by that? Well, remember, since we're dealing with a definite integral, we're looking for the area underneath the curve on the interval from -1 to 1. So the key here is to recognize the curve that we're working with. So let's go ahead and take a look at the integral one more time. So we have the integral from -1 to 1 of the square root of 1 minus x squared. Okay, so what I'm going to do here is define the y to be the square root of 1 minus x squared. Okay, now squaring both sides, we will get here y squared is equals to 1 minus x squared. Now adding x squared to both sides, we're going to be left with x squared plus y squared is equals to 1. Now hopefully you guys recognize this equation as the equation for a circle with a radius of 1, which is also centered at the origin. Okay, so visually, we can go ahead and draw in our circle. Alright, now since we're dealing with the positive square root of 1 minus x squared, then that means that we're only dealing with the upper half of the circle. So we're looking for this area then. Well, if you remember your geometry formula, the area of a circle is equals to pi times the radius squared. Now in this case, we're dealing with a circle of radius 1, so the area for the full circle is going to be pi. However, since we're dealing with only the upper half of the circle, then our area is going to be equals to 1/2 times pi, or pi over 2. So putting everything together then, we're going to have the integral from -1 to 1 of the square root of 1 minus x squared is going to be equals to 1/2 times pi times the radius squared, which is simply pi over 2. And there we go. So you see, for this problem, there were no new integration techniques that we used. It was just a matter of recognizing what we meant by a definite integral and what was the curve that we were working with so we could figure out the area underneath it. Now, the problem with this type of integrals, though, arrives when we don't really have a definite integral. Because if we get rid of the bounds then, well, we wouldn't really know what would be the radius of the circle, so we really wouldn't know how to do this problem. And this is where the new technique of trigonometric substitution will come into play. Now, before we get into the technique, though, I want you guys to recall a few of the trigonometric identities that we have seen in class so far. So we have the Pythagorean identities, the double angle identities, half angle identities, and lastly, the Pythagorean theorem. Now, before we proceed, though, I want you to pause the video and write down the identities that you remember. As we continue on with more integrals involving trigonometric functions, it is vital that you feel comfortable with these formulas. So I'll let you pause the video now, and when we resume, you can compare your answers. Alright, so let's pause. Welcome back. So hopefully you got a couple of them down. So let's recap here. The Pythagorean identities are the sine squared theta plus cosine squared theta is equals to 1, tangent squared theta plus 1 is equals to secant squared theta, and lastly, 1 minus cotangent squared theta is equals to the cosecant squared of theta. Now, as I mentioned in previous recordings, really, the only Pythagorean identity that you need to remember is the sine squared plus cosine squared of an angle is equals to 1. The other two come from this formula. You just need to divide by either a cosine square or a sine squared. Now, for the double angle identities, the easiest one to remember is the sine of 2 theta being 2 sine theta times cosine theta. And the cosine of 2 theta, it has 3 different forms. Depending on the problem, one of them may be more useful than the others. And lastly, ones that are hopefully a little bit more fresh in your minds are the half angle identities, since we used them in the previous lecture involving the trigonometric integrals. Alright, so now let's take a look at the Pythagorean theorem. Now I know that most of you guys remember the Pythagorean theorem as a squared plus b squared is equals to c squared. Now what does this mean? Well, you might remember that a Pythagorean theorem is dealing with a right triangle whose sides are A, B, and C. Now remember that the Pythagorean theorem is telling us that the sum of the square of the sides of a right triangle is equals to the hypotenuse squared. Basically what we have in this diagram here. Now, since the Pythagorean theorem will be crucial for this lecture, I want you guys to think about it a little bit more in depth so we can take full advantage of it. So for example, let's say that I didn't know the hypotenuse and I didn't know the length of one of the sides. So can we figure out the length of the other side? Well, we can. If we go ahead and take the Pythagorean theorem and solve for one of the sides, I'll solve for b in this case, then we can have here that b squared is equals to c squared minus a squared. Okay, now this one here is telling us the length of the side squared, but what is the actual length of the side? Well, all that we would need to do here is simply take the square root of both sides, and that's going to tell us that the side b is equals to c squared minus a squared. In other words, is the square root of the hypotenuse squared minus the length of the other side squared. Okay, now what if we actually want to figure out the length of the hypotenuse? Well, the length of the hypotenuse would then be c is equals to the square root of a squared plus b squared. Right now at this stage, I want you to notice something. If we wanted to figure out the hypotenuse, we were taking the square root of a squared plus b squared, so you were taking the square root of a sum of squares. Now, if you wanted to figure out the length of the triangle, well, then you had the square root of c squared minus a squared, which was a difference of squares. Now, it was a difference of squares, but also notice here, importantly, that it was a difference of squares where you were subtracting the length of a side squared from the hypotenuse squared. And this here is always the case. Now, the reason that I'm emphasizing the Pythagorean theorem here is because when we're working with integrals involving trigonometric substitution, the key idea is going to be to use the Pythagorean theorem in order to manipulate the integral. Now I know that if you take a look at your textbook or maybe other videos, then you can see here that trigonometric substitution seems to be a problem where you are going to be using certain formulas. But I don't want you guys to think about those formulas as the end-all be-all. I want you to do this type of problems without the need for memorizing formulas. And in order to do so, you will be using the Pythagorean theorem and you will need to draw triangles. When it comes time for quizzes or exams, I will require you to draw the triangle so you can do the integral. This leads into a more fundamental understanding. Alright, so without further ado, let's go ahead and take a look at our first problem involving trigonometric substitution. Now before we begin though, I do want to mention something. For these problems, we'll be assuming restrictions or appropriate restrictions for the x values so that our answers are real numbers. Alright, so with that said, let's take a look at the first example here where we have the integral of the square root of 1 minus x squared, dx. So it's the same integral that we started this video, but this time around, well, we don't have any bounds. So what can we do here? Well, when I take a look at this integrals, I notice I have a square root of a difference of squares here. Now, we discussed above with the Pythagorean theorem, well, if we have the square root of a difference of squares, it seems like what we actually have here is the side of a right triangle. Well, in that case, then what I'm going to do here is I'm going to go ahead and draw a right triangle. Okay, so now that I have our triangle here, I'm going to go ahead and label the acute angle here theta, and I'm going to go ahead and label the sides. So we're going to have here our hypotenuse C, our side A, and our side B here. Alright, so let's go ahead and label them. So what is our A, our B, and our C? Well, again, going back to the Pythagorean theorem, if we have a squared plus b squared is equals to c squared, let's go ahead and solve for, let's say, a. So that would give us here that a is equals to c squared minus b squared, but we are square rooting here. Okay, now comparing this to our original integral, or at least the square root, where we have 1 minus x squared, well, we get to see here that it seems like our c squared is equals to 1, which means that our c is equals to 1. All right, so we have c. And we can also notice here that b squared seems to be the same thing as x squared. So we know that our b is equals to x then. Okay, well now our a squared, or sorry, just the a by itself, is going to be the square root of 1 minus x squared. Alright, so now that we define our triangle here, now comes time for the trigonometric substitution. And here's how it goes. originally we had the integral of the square root of 1 minus x squared dx. But we want to go ahead and write all of this in terms of trigonometric functions. So how can we do that? Well, you know that the square root of 1 minus x squared corresponds to the adjacent side of this right triangle. But we know that the adjacent side of a right triangle is associated with the cosine of the adjacent angle. So we have here then that the cosine of the angle theta should be equals to the side adjacent, which is the square root of 1 minus x squared, divided by the hypotenuse. Now lucky for us, the hypotenuse is 1, so we can go ahead and replace this integral, or the square root of 1 minus x squared, with the cosine of the angle theta. Okay, now that takes care of the square root, but we have another big problem. What about this dx? Since we're rewriting everything in terms of trigonometric functions in terms of theta, we don't really want a dx in our problem. Instead, we want a d theta. So how can we get the d theta? Well, what we can do here is make use of the fact that, hey, we have knowledge of x in terms of theta. You might be wondering, but wait, which knowledge? Well, we do know that the side opposite to the angle theta is x. So what we can do here is then say that, okay, well, sine of theta is equals to x over the hypotenuse. Now lucky for us, it's 1 here. All right, so rewriting this one here, I'll just switch the order. I have that x is equals to the sine of theta. Now at this point, we are going to be using differentials to figure out what is dx in terms of the theta. Very similar to the way that we were using differentials whenever we used a u substitution. We define our u, then we found the u in terms of dx. Now for this example, since it might be a little bit weird, I'm going to go ahead and break down the process a little bit more. So I'm going to go ahead and take the derivative here of both sides with respect to theta, because again, we see here that x is a function of theta. So d theta of x is equals to d theta of the sine of theta. Alright, so this one here then is going to give us the x d theta is equals to, well, the derivative of sine with respect to theta is equals to the cosine of theta. And at this point, we can now go ahead and multiply by our d theta on both sides. And this is where the differentials were coming into play. So you get to see here that dx is equals to cosine theta d theta. And this is the final piece of the puzzle. Well, at least in terms of the trigonometric substitution. Alright, so now our integral then is going to be the integral of the cosine theta times cosine theta d theta, which is then going to become here the integral of cosine squared of theta d theta. Okay, well, look at that. We're left with the integral of a cosine squared. Now, you might recall the techniques discussed in the previous section involving trigonometric integrals, so we know that we can go ahead and perform the power reduction formulas in order to rewrite this integral as the integral of 1 plus the cosine of 2 theta divided by 2 d theta. So this one here is going to give us the integral of 1/2 d theta plus the integral of 1/2, well, 1/2 times the integral of the cosine of 2 theta d theta. Performing the integral here, we're going to have 1/2 theta plus 1/4 times the sine of 2 theta plus c. Now, at this point, you might be wondering if this is our final answer, since, well, we finished evaluating the integral, but the thing is, though, that our original integral was in terms of x. The result that we got right now was in terms of theta. So what can we do? Well, now, this is the last and final step. We need to go ahead and rewrite our answer in terms of the original variable. Alright, so there are two terms to consider, a 1/2 theta and a 1/4 times the sine of 2 theta. So I'm going to focus on the 1/2 theta first. And lucky for us, our triangle is going to come to the rescue one more time. So remember that we defined sine of theta as x. So I'm going to go ahead and take a look at that equation. Sine of theta is equals to x. Now I'm going to go ahead and take the sine inverse, or the arc sine of both sides of the equation, and we're going to be left with theta is equals to the arc sine of x. Alright, so we know what theta is now in terms of x. It's the arc sine of x. But now let's take a look at the other term. What about the 1/4 sine of 2 theta. Can our triangle come to the rescue in this case? Well, unfortunately no, because our triangle here was only in terms of theta, not 2 theta. Nonetheless, I do see that I do have a double angle, so we can go ahead and use our double angle identities here. So if you recall, the double angle identity for the sine of 2 theta is going to be 2 times sine of theta cosine theta. Now there's a 1/4 in the front, so I'm going to go ahead and cancel this ones. So we're going to be left with a 1/2 times the sine of theta cosine theta. And there we go. Now we don't have a double angle. Nonetheless, we still have our results in terms of theta. But this is now where the rewriting is going to come into play. So I'll write this one here. We're now going to have a 1/2 times theta, which we know is the arcsine, plus a 1/2. But now, for the sine of theta, well, we know that the sine of theta was equals to x. There we go. Let me put it in blue. So this one here is x. Now what about the cosine of theta? Well, the cosine of theta was defined here as the square root of 1 minus x squared. Okay, now with all these substitutions, we no longer have any thetas. Everything is in terms of x. So the last and final thing to do here is to add a c. And there we go. We would be done. This is the method of trigonometric substitution. So let's recap what we did real quick. So when we took a look at the integral, we recognized that it was an integral dealing with the square root of a difference of squares. That was an indication that, hey, a right triangle might be able to help us, since this is the way that we're defining the length of a side of a right triangle. Now, once we do the triangle, we identified the other pieces of the triangle, namely the hypotenuse, and as well as the other sides of the triangle. Now, once you define the sides in terms of x's, that's where the trigonometric substitution come into play, because you could have rewritten the sides in terms of trig functions. That's how we obtained the cosine and a sine. Next, we rewrote the original integral in terms of the trigonometric functions, taking note that whenever we had a dx, we needed to use differentials with the theta, so that we obtain an expression for the x in terms of the theta, so that we're able to rewrite all of our integrals in terms of thetas and d thetas. Afterwards, we did need to use some of the formulas that we encounter for the trigonometric integrals, namely the power reduction formulas, that was allowing us to rewrite our integral here into something that we can actually integrate. However, once we integrated everything, we were left with expressions in terms of theta. So the last and final thing that we did was to, again, make use of the fact that we have a triangle that was relating x's and thetas. So that's how we obtain our final answers in terms of x. Now, before we move into another problem, I want to revisit this problem again, but take a look at it from a slightly different perspective. I'm going to go ahead and do this one here on the side. All right, so we were dealing with the integral of the square root of 1 minus x squared. All right, so just as we began before, I'm going to go ahead and draw a right triangle here. So here we have a right triangle, and I'm going to go ahead and label the sides, my A, the B, and the C. Now the C is the hypotenuse. Well, it was still 1, but you might have been wondering in the previous example, why did I define the B to be x and not the A to be x? Does it matter? Well, let's see. In this example, I'm going to go ahead and define the A to be x and the B instead to be the square root of 1 minus x squared. And let's see if it makes a difference. Okay, well, now that we defined the sides here, I'm going to go ahead and define the angle, theta. Okay, now in this example, we get to see here that the sine of theta is the one that is equals to the square root of 1 minus x squared all over the hypotenuse, which was 1, and the cosine of theta is the one that is x here. Okay, now go ahead and, to go ahead and rewrite the integral in terms of trigonometric functions, we're going to have here the integral of the sine of theta, but what about the dx? Well, just as we did before, I'm going to go ahead and write x is equals to the cosine of theta, now with the differential, taking the derivative with respect to theta, we're going to have dx is equals to, now I have a negative sine of theta d theta. Okay, now rewriting our dx, we're going to have here a negative sine of theta d theta, which is going to give us a negative integral of sine squared of theta d theta. Now we still need to go ahead and use our half angle formulas or the power reduction formulas, which will give us a negative times the integral of 1 minus the cosine of 2 theta all over 2 d theta, which is giving us a negative 1/2. I'll put the integral there. Integral d theta plus 1/2 the integral of the cosine of 2 theta d theta. Performing the integral then, we're now going to have here 1/2 theta plus 1/4 times the sine of 2 theta plus c. Okay, now before substituting back everything in terms of x, I'll just simplify the sine of 2 theta. We're going to have here a negative 1/2 theta plus 1/2 sine of theta cosine theta plus c. And again, guys, I'm doing the same work as we did before, just doing a little bit faster. Okay, now at this point we can go ahead and back substitute. Now once we back substitute, notice that the first term is going to be a little bit different. It's now going to be a negative 1/2, but theta, well, since theta was defined here, or cosine of theta was x, we can go ahead and obtain theta by taking the cosine inverse, or the arc cosine. So we get to see here that theta is equals to the arc cosine of x. Okay, so we're going to have here a negative 1/2 times the arc cosine of x plus, we're going to have a 1/2. Now sine theta was also defined differently. Sine theta was the square root of 1 minus x squared. Now the cosine of x, as we said before, was defined as x. So we're going to have here a plus c. So now let's compare our answers. Well, when we compare the answers, notice that the 1/2 x times the square root of 1 minus x squared remained the same. That did not change. However, the first term, originally we had a 1/2 times the arc sin of x, but if we define the triangle a little bit differently here, we're going to have a negative 1/2 times the arc cosine of x. So what happens here? Does that mean we're wrong? Does it matter if you choose a different side of the triangle? Lucky for us, guys, it doesn't really matter. These equations are the same. Now, if you actually wanted to graph them to see how they look, you would see that you're seeing the same graph, except that it's off by some vertical shift. That vertical shift is taken into account by this constant of integration here. But if you actually perform the definite integral, both of these answers will give you the same area. So it doesn't really matter how you define your triangle, as long as you're defining, well, I would say as long as you're defining the hypotenuse correctly in this case, but I do want to mention the reason that I defined the x as this side first. The reason for that here is, if I define the x to be the side opposite, once I start to think about the differentials, well, now I have the sine of an angle is equals to x. The reason I prefer this one is because the derivative will not give me any negatives. Sometimes negatives are easier to lose track of, so if you can avoid negatives, avoid negatives. If you define the x here to be the side adjacent, once you're finding the differential, you'll see here that you're left with a negative, and I don't want that. All right, so this is it for part 1 of the video. It was just an explanation of what we're doing with the trigonometric substitution, and as you saw here, it was all about right triangles. So in the next set of videos, we're going to be taking a look at more examples and define the triangles in a way that we sometimes may need to use a tangent or other of the trigonometric functions. I'll see you there.